extension lecture of time response specifications of second order system. Okay, I start with the sum, that is very interesting sum. The system is given by a differential equation. A system is given by differential equation. Differential equation d square y of t divided by dt square plus 4 dy of t by dt plus 8y of t is equal to 5x of t. Here y of t is output and x of t is input. Okay. So here what he has asked to find once again TR, PP, MP and C of t, time response. It's a 10 to 12 marks problem. First I want zeta and omega n. Zeta and omega n are very important. These are called behavioral characteristics of second order system. How to find a zeta and omega n? Once I know the transfer function, I can find. First I will find the transfer function. So I know that d by dt is equal to s and d square by dt square is equal to s square and t equal to s. How to convert time domain into Laplace domain or Laplace transformation. So now this is the given second order differential equation. Now you take a Laplace transformation, d square x square y of s plus 4s y of s plus 8y of s equal to 5x of s. So y of s equal to s square 4s plus 8 equal to 5x of s. Now Laplace of output divided by Laplace of input equal to transfer function. So that what I will do, I will take a Laplace of output, that is y of s divided by x of s equal to 5 divided by s square plus 4s plus 8. This is a transfer function. Now from this transfer function I will find zeta and omega n. How to find zeta and omega n? Comparing with standard form of second order closed loop transfer function. Now, so here also s square coefficient is 1, here also s square coefficient is 1. Okay, this is a standard form. You compare denominator, you don't compare numerator. Sometimes it may be 10. Don't compare numerator, you compare only denominator. Omega n square is equal to 8. Omega n is equal to root of 8. Okay. That is 2 root of 2 radian per second. And 2 zeta, compare s coefficient. 2 zeta omega n is equal to 4. Zeta is equal to 4 divided by 2 omega n. 4 divided by 2 into 2 root of 2. 4. 1 by root 2. That is zeta is equal to 0.7067. Now I suppose to find theta. Theta equal to tan inverse of root of 1 minus zeta square divided by zeta into pi by 180. That is equal to tan inverse of how much zeta? 0.76 divided by 0.767 into pi by 180. So theta equal to that is pi by 4. theta is equal to pi by 4 radians. I'll find omega d. Next is damped natural frequency. Damped natural frequency is equal to omega d root of 1 minus zeta square, that is omega n is how much omega n? 2 root of 2 into root of 1 minus zeta is 0.7067 whole square, that is equal to 2.02 radian per second. Now what he has asked, once again, rise time. This is a formula for rise time. Pi by 4 divided by omega d is 0.02. That is the rise time. And peak time, Tp equal to pi by omega d, pi by 2.02 seconds. And next is MP. Okay, you calculate and write down. MP equal to E minus pi zeta divided by 1 divided by root of 1 minus zeta square into 100. So E raised to pi zeta 0.7067 divided by root of into 100. We will get in percentage, 4.33%. And settling time is equal to 4 divided by zeta is this, and omega n will get some seconds. Okay, so TR, rise time, peak overshoot, and settling time. And very important in this problem, he has asked the C of t, time response, C of t. C of t. C of t equal to 1 minus e raised to zeta omega n t divided by root of 1 minus zeta square sine of theta plus omega or omega dt plus theta. So C of t equal to, I know the values, zeta is 0.7067, omega d into t is the time, 1 minus 0.067 whole square sine of omega d is 2.02 t plus theta is pi by 4 radians. So C of t equal to 1.41 e raised to minus 2t sine of 2t plus pi by 4. 2.02 I have written 2. So this is the time response. You can find t equal to 1 second, what is the C of t? T equal to 2 seconds, what is the C of t? You can find this, but while operating, this is already in radian, sine should be in the radian mode. That care you have to take, sine should be in the radian mode because inside term is already radian. Okay, from the differential equation, how we find out the transfer function? From the transfer function, we calculated zeta and omega n, then omega d, then theta, then TR, TP, MP, TS, and C of t also. Next problem. Next, very interesting and very typical problem. Find the value of A. Find the value of A for g of s equal to k divided by s into bracket s plus t to reduce MP, maximum peak quotient MP, 75% to 25%, where P is time constant and K is also where P and K are constants. Okay, solution. So here MP he has given, so that first I will apply the formula for MP. MP has given. Two MPs are given. Initially MP is high, now I want to reduce. You know that MP is inversely proportional to zeta. You know, when the zeta increases, definitely the MP from the formula. So now I'll apply MP is equal to, the formula is pi zeta root of zeta square. Let us, I'll take for this MP zeta 1 and one more MP, this is for zeta 2. What is the first MP? 0.75, because I have not written 100. So here now 0.75 log BC is equal to minus zeta 1 root of 1 minus zeta 1 square, and here also log BC is equal to zeta 2 root of zeta 2 square. Now log BC 0.75 divided by pi and whole square, squaring both sides, quadratic equation, one unknown, okay, that is pi, squaring both sides, you will get zeta 1 here, zeta 2. Definitely zeta 1 is less because MP is high, zeta 2 is more. Now zeta 1 is 0.911 and this is 0.037. Just to check the values. Two MPs are given. I want to reduce this MP to this MP. Always MP should be less, it is a better. For that you have to increase the zeta from 0.0911 to 0.4037. But in the problem what he has asked, find the value of new gain. For this one gain, for this one more gain. So definitely the gain is reducing. Once again it is inversely proportional. Zeta to gain is also inversely proportional. So now what I will do, I have got zeta 1 and zeta 2 values from the MP. Now I will see this G of S, and definitely he has given H of S is 1 unity feedback. If I know G of S and H of S, what I supposed to calculate? Here I have to calculate transfer function. Why I supposed to calculate transfer function? Because I need a zeta and omega n. Whenever we are solving the problem in the second order system, we need zeta and omega n. So that what I will do, C of S divided by R of S equal to G of S divided by 1 plus G of S H of S. This is standard formula, because suppose this is G of S, this is R of S, C of S, this is minus, this is H of S. It's called minor feedback loop. Whenever there is a minor feedback loop, here if this is a minus, then feed forward element divided by 1 plus feed forward element into feedback element. Here I know G of S value, it is given in the problem, and H of S is also given in the problem. So here k divided by s equal to s plus t divided by, I'll take a LCM, s plus t. Now s plus t get cancelled. So k divided by s square ts plus k. I can write s square ps plus k. Now I'll find here omega n and zeta, comparing with standard form of second order transfer function. Comparing with second order transfer function. Okay. What I supposed to write here? C of s divided by R of s equal to k divided by s square plus ps plus k. Now you compare omega n square is equal to k, so that omega n equal to root of k radian per second, plus or minus you consider plus. You are compared with constant. Now you compare with s coefficient, 2 zeta omega n equal to capital T, zeta is equal to t by 2 omega n. I know that omega n is root of k. I know that root of k. So now I got a zeta value. But I have 2 zeta value. This is a 75% empty, this is 25% empty. Now I'll apply this formula. I'll take zeta 1 equal to 0.0991. Zeta is nothing but t. In this case, t is a constant and k is the value. K becomes k1. K becomes k1 because zeta is equal to zeta 1, that is equal to 0.001. So now 2 divided by 0.09191 root of k1, squaring both sides, t square divided by 4.0991 whole square. This is equation number 1. Okay, when this is the gain, then this is the zeta, or this is a zeta, you will get this is the gain, and MP 75%. Now I'll consider for case 2. This is a case 1. The case 1 is MP is equal to 75%. Case 2, MP equal to 25%. In this case, once again, zeta 2 equal to 0.037, Zeta, the formula we got, zeta is equal to t divided by 2 root of k2. Now t divided by 2 into 0.037 root of k2, and k2 squaring both sides, t square divided by 4.437 whole square. This is equation number 2. Just what I will do, dividing equation 2 by 1, dividing equation 2 by 1, dividing equation 2 by 1, now t square get cancelled. The formula is 0.05, means the final k2 is equal to 0.05 of k1. Gain will be less. Suppose initially gain was 100, now gain is 5. So from this problem you understood zeta when inversely proportional to zeta, and zeta is also inversely proportional to gain. It's a very contradictory one, because always in the problem I need high gain and less MP to set a one optimum value of zeta. If you set a less value of zeta, then MP is high, and it is not good, but gain is high, it is good. But if you go for higher value of zeta like 0.7, 0.8, 0.9, then gain will be less and MP will be less. So that somewhere you should have a moderate value of like 0.6 or in between 0.55 to 0.65. The best value is 0.6 for a dead damping case. Okay. Okay, in the next lecture, I'll solve some more two problems in the next lecture. Okay, thank you.